Okay, Chemistry 3111. We are going to start out with Chapter 20 right now, which is carboxylic acids and their derivatives. Now, I don't have a good enough memory. I'll probably forget some of the derivatives, but you guys all know what a carboxylic acid is by now. And there's a lot of things you can do with a carboxylic acid. But when it says their derivatives, that means we're going to talk about esters, we're going to talk about acid, chlorides. We're going to talk about acid anhydrides and hydrides. Amides are going to come up in this chapter. And then I would also say nitriles are going to show up in here. And then, of course, etc. Right? We're going to look at other functional groups as well. But these are some of the functional groups that show up in this chapter. All right, so there's a lot of different parts to the carboxylic acids chapter because we're dealing not only with carboxylic acids, but their derivatives. And what's cool is that carboxylic acids are actually really abundant in nature. They're found all over the place in different naturally occurring compounds. And so here are some examples. The first one is acetic acid. Okay, you have to memorize the name acetic acid, and I'll talk to you more about that later on. But if you've ever smelled vinegar, the part that kind of stings your nose or whatever, that is acetic acid. There's also water in vinegar. It's not pure acetic acid. Then butanoic acid. So it says here, responsible for the rancid odor of sour butter. I would also say that vomit, the smell of vomit, is butanoic acid. Hexanoic acid, responsible for the odor of dirty socks. Kind of a funny one. But yeah, so that's another carboxylic acid. And I know that a lot of you, not all of you, but I know that many of you have studied advanced biology and you've studied aerobic oxidation and anaerobic oxidation. So you've studied the production of lactate. And so lactic acid is just the conjugate acid of lactate. And that's responsible for the taste of sour milk. So if you ever drank some rotten milk by accident. What else we see on here? You guys know what aspirin is, right? Aspirin is acetyl salicylic acid. So you see there's a carboxylic acid in that. Also, this cool compound that's used for the treatment of TB, tuberculosis, is a carboxylic acid. And then even things like this anti-acne compound here has a carboxylic acid in it. Now, in terms of, everyday chemistry that's going on around us in our country, the U.S. actually produces around 2.5 million tons. 2.5 million tons of acetic acid per year. If you're like, that's a lot of vinegar, Mr. Dion, what are we doing with all that? Well, it's actually mostly used to make vinyl acetate. So what they do is they heat up methanol and carbon monoxide with a catalyst, and that makes acetic acid. But again, most of it goes to make vinyl acetate. And if you're going, well, I've never even heard of that. What's that used for? Good question. It's actually used in paints, okay, and adhesives as well. But when you buy some Behr paint or some Sherwin-Williams, if you're a high roller, vinyl acetate is found in paints and adhesives. So let's see here. Carboxylic acid derivatives. What's the take-home message? Is that they're very, very common, hugely common, and they play a central role in organic chemistry. And what I was telling my students today is just before I started recording this video, I said, a good organic chemist, man, oh man, when we see a carboxylic acid, and I'm not lumping myself in with good chemists, but anyhow, when a seasoned chemist sees a carboxylic acid, she or he usually gets excited because there's so many things that you can do with a carboxylic acid. Now, if you're naming a carboxylic acid, okay, to name a carboxylic acid, all you have to do is take the suffix E off of an alkane. You drop that and you replace it with oic acid. So let me show you what I mean. If you had 1, 2, 3, 4 carbons, I mean, obviously you guys know that this is butane, okay? So if you convert one of the carbons on the end to a carboxyl group, it becomes butanoic acid. So you would have methanoic acid, ethanoic acid, propanoic acid, butanoic acid, pentanoic acid, so on and so forth. And you see this compound over here, which has 2 functional groups. It's got a carboxylic acid in it, and it also has an alcohol in it. Now, if you're wondering, what would I call this compound? Do I call it a carboxylic acid, or do I call it an alcohol? Well, if you look at this chart over here, this is called the order of priority of functional groups in organic chemistry, or sometimes they call it the order of precedence. But you see that the king of the castle, the ruler of all of them, is the carboxylic acid. Nothing takes more precedence, or nothing is higher in the hierarchy than a carboxylic acid. So you would not call this compound an alcohol. You would call it a carboxylic acid. And you can see that the suffix, we always use the parent, or the parent functional group. And so this is a 5-hydroxy 4,4-dimethylpentanoic acid. You do not have, I actually took this out of the appendix of our textbook, believe it or not. You do not have to memorize this. What I tell my students for our level is that you probably notice that all the functional groups that contain oxygen, they have a higher order than alkanes, alkenes, and alkynes, okay? Except for the lowly ether. But anyhow, anything that contains a carbonyl and an alcohol. Anyhow, but again, you don't have to memorize it for our class, so don't stress about it a whole lot. All right. Now, if we have a carboxylic acid group that's attached to the ring, okay? You guys remember this one from chapter 19, that when you had something like this with an aldehyde, if you remember, we called this cyclohexane carbaldehyde. Well, it's something in the same vein with carboxylic acids. You would call this compound cyclohexane carboxylic acid. And if you're wondering what, you just write the word carboxylic acid. Yes, that's what you do when you're dealing with a ring and your carboxyl group is attached to it. Now keep in mind, this is not an aromatic ring. If you have an aromatic ring, right, if you have a benzene ring, okay, and then you append a carboxyl group on it, that's benzoic acid, okay? So don't mix up these two compounds. They are completely different. All right, so cyclohexane carboxylic acid, excuse me. There are also many common names for carboxylic acids that you need to know. So I told you that if you have one carbon, you would call this methanoic acid, right? That would be the systematic name. The common name is formic acid, and that comes from the Latin word, I don't know, for me or something, which has to do with an ant. The next one is acetic acid. Its systematic name would be ethanoic acid. The next one is propionic acid, and it's propionic acid, but its IUPAC name would be propanoic acid. I guess these are both IUPAC. I would just call the one in blue the systematic name. Butyric acid, its systematic name would be butanoic acid. Butanoic acid. Then if you have 5 carbons, it would be pentanoic acid or valeric acid. Either one is fine. And then we have benzoic acid on here. So if you're wondering, do I have to know ethanoic acid and acetic acid? I would say yes. It can be annoying for students to, you're like, I have to do that for all these different compounds. Yes. The reason why is these compounds, these little carboxylic acids, show up so much in organic chemistry, and we as chemists, we use the words interchangeably: propanoic acid, propionic acid, butyric acid, butanoic acid. Okay, so it is something that you want to be aware of. Now, if we have dicarboxylic acids like malonic acid or succinic acid, again, I know that a lot of you have studied biology at a high level, and you've heard of things like succinate, right, and glutarate when you study the Krebs cycle and glycolysis and all those kinds of biological pathways. And so some of you have been exposed to these dicarboxylic acids already. If not, that's totally fine. If you have, let's say, 2 carbons, you could just call this, you could call it ethane dioic acid, but the common name is oxalic acid. If you have 3 carbons, you could call it propane dioic acid, which is fine, but the common name is malonic acid. If you have 4 carbons, you would call that butane dioic acid, but the common name is succinic acid. And then you can see that for pentane dioic acid, its common name is glutaric acid. Now, if you have 6 carbons, so let me just scribble this down here. So if we had 1, 2, 3, 4, 5, 6, this one you would call it hexane dioic acid, but it has a common name too, which is adipic acid. Adipic acid. And the reason I throw this one in here is because years and years ago, my students came up with an acronym to remember: OMSGA for oxalic, malonic, succinic, glutaric, and adipic. And it is this. It was, oh my stars, go away. Okay. I think that was the first class I ever taught at UCCS. My students came up with that beauty. Okay, so oh my stars, go away. To remember the dioic acid. So again, if you go in the textbook, okay, I swear on the Bible, okay, it says right in there that these names have to be committed to memory. The dicarboxylic acid. It's something we all have to memorize. And again, it'll help you in your biology class. And I know that a lot of you are going to take biochemistry right after this class. So let's see if we can provide an IUPAC name for these compounds. And these are not meant to be mind bogglers or anything. It's just kind of fleshing out the idea here. So the first one's got a total of what, 5 carbons in it. So yeah, you don't really need my help for this one. So let me see here. Let's do it like this. Okay, so we've got 1, 2, 3, 4, 5. So, I mean, these are on the last slide. So you could call it pentane dioic acid. So pentane dioic acid. And I said it was oh my stars go. So, or you could call it glutaric acid. Let me check one quick thing before I move on about this question. I do have one question that I'm not 100% sure. I'm going to have to check the textbook. Yeah, okay, looks good. The way we've named it is fine. The next one has a total of how many carbons in it? Let's see here. It's got a total of 2, 3, 4 carbons. And so, oops, go. So if I have 4 carbons, so that's going to look something like this. So 1, 2, 3, 4. So I can call this, I could call it butanoic acid, right? You take butane, you knock off the E, and you call it butanoic acid. But the common name for this compound is butyric acid. So with a Y, butyric acid. And the last one, okay, we have an aromatic ring. Okay, that's with this. So C6H5. C6H5 is aromatic. That's monosubstituted. And then we have our carboxyl group like this. So this would be benzene carboxylic acid if you wanted to use the systematic way. So benzene, carboxylic acid. Okay, so we name the ring, then we say carboxylic acid, but nobody would ever call it that. What do we call it as chemists? We call it benzoic acid. There you have it, my friends. A little nomenclature of some carboxylic acids. We're just getting warmed up, though. You know something I found when I was a student? I like these kind of questions more, where it gives you the name and you have to come up with a structure. Found there was a little less room for error. So it says cyclobutane carboxylic acid. So if it's cyclobutane, that means I have a 4-membered ring, just a square like that. It's hip to be square. And then we would just put our carboxyl group like that. So that's cyclobutane carboxylic acid. The next one is 3,3-dichlorobutyric acid. So butyric acid has 1, 2, 3, 4 carbons, right? The carbon that has the carbonyl on it, the carboxyl carbon, that's going to be carbon number 1. And so if we have 1, 2, 3, we're going to have, we're going to have 3,3-dichloro. Like that. And the next one is glutaric acid. So, oh my stars, go away. So 2, 3, 4, 5, 6. So five carbons in glutaric acid. So we have 1, 2, 3, 4, 5. That's better. Like that. So there's my glutaric acid. And then I need 2 methyl groups at carbon number 3. Not my best artwork there on that carbonyl. Anyhow, you get the idea. Something like that. Give me a thumbs up if you're with me on naming these compounds. Any questions about those? No? Okay, nothing too earth-shattering in there. Let's try a couple more. We'll up the ante a little bit. We'll make it a little more complicated. So remember, when you're naming a carboxylic acid, you want to find the longest carbon chain that possesses the carboxyl group. So 4, 5, 6. So this is some kind of hexanoic acid. And then we have 4 methyl groups, 3, 3, 4, 4 tetramethyl. So we would call this 3, 3, 4, 4 tetramethyl hexanoic acid, like that. Let's see. The next one is longest chain is 1, 2, 3, 4, 5. So this is a 2-propyl pentanoic acid. So 2-propyl pentano. Come on, computer. Pentanoic acid. You could also call this one a valeric acid too. That would be fine. So you could also call this 2-propyl valeric acid. That would work too. And the next one is actually an amino acid. This is, has anybody here had to memorize the amino acids for any classes? This is L-phenylalanine. Phenylalanine. No? Okay. You will have to memorize the amino acids in biochemistry. So in biochem must know all amino acids. And that's something that we're going to take a look at towards the very end of this class. We're actually going to do a chapter where we talk about amino acids, peptides, and proteins, and primary structure, secondary, tertiary, quaternary, all that stuff. But anyhow, if we wanted to name this compound, first of all, could anybody tell me, is this an R compound or an S compound? And it's not a trick or designed to fool you or anything. It's not a getcha question. Could anybody tell me, is this an R compound or an S compound? Yeah, thanks, Erica. It's an S compound, isn't it, right? Woo, like this. So yes, this is an S compound. So Erica got it. So it's S something. So I'm going to scribble this off here, Erica. And we'll just start with the number 1 on the carbonyl carbon. So 1, 2, 3. So this is a 2-amino. So that's what we call an NH2 group. It's a 2-amino, 3-phenyl propanoic acid. So we'd call this S. And it's going to be 2-amino, 3-phenyl propanoic acid. Propanoic acid, or you could call it 2-amino 3-phenyl propionic acid, 3-phenyl propionic acid. Either one is fine. All right. So that's naming just carboxylic acids. We're going to take a look at the derivatives in a little bit. Well, we're not quite there yet. We want to spend a little more time talking about carboxylic acids. You know, sometimes I'll ask my students in class when we're in person on campus, I'll say, you know, what are some things you know about carboxylic acids? You know what they always bring up is the IR, right? You guys remember the carboxyl group, right? You had the oxygen hydrogen stretch in the IR that's from what, like 3,400 all the way down to 2,200 reciprocal centimeters. It's like the first functional group you learn to recognize in the IR. But the reason why that stretch is so broad is because of the intense hydrogen bonding, and you can see that there's, you know, hydrogen bonding is maximized, you know, between acetic acid pairs. Also, you should know that the carbonyl carbon is sp2 hybridized, and therefore it's trigonal planar. And so because carboxylic acids can form these, you know, extensive hydrogen bonds like this, okay, this we sometimes call it a dimer when they bond together like this. That's why acetic acids have even higher boiling points than alcohols. Like, let's say you compare acetic acid, which has 2 carbons, versus ethanol, which has 2 carbons. Acetic acid has a higher boiling point. Like, I don't have it written in here. I thought maybe I did. But let's say you compare, so I'll put them here. So ethanol has a boiling point of about 78 degrees Celsius, whereas acetic acid has a boiling point that is 118 degrees Celsius. Okay, so it's got a really high boiling point. And again, it's because of this extensive hydrogen bonding. So, wow, this is really a blast from the past. If you go all the way back to chapter 3 in our textbook, back when we talked about acids and bases. Okay, well, it's back. Okay, now, hopefully you remember that the pKa of an alkyl carboxylic acid starts around 5. Like acetic acid has a pKa of 4.75. And so if you take a carboxylic acid and you put it in a strong base like sodium hydroxide, well, the carboxylic acid is your acid and water is your conjugate acid. And the pKa of water, son of a gun, the pK of water, I was just getting warmed up there. The pK of water is around 16. I'll just put here 15.7. So the equilibrium is going to lie to the side of the carboxylate salt, right? You have a difference. 15.7 minus 5 gives you more than 10. So that means that bases like sodium hydroxide are going to be very effective at deprotonating carboxylic acids and converting them into carboxylate salts. Remember the word salt for chemists. Salt doesn't necessarily mean sodium chloride when you're a chemist. It means you've got a cation and an anion, some kind of ionic compound. Now, if you want to name a carboxylate salt, this is another bit of naming that you have to do. And the way you name a carboxylate salt is you replace the E suffix with O8, okay? So if you have benzoic acid, you remove the ic acid and you replace, or you remove the oic acid really, and you replace it with O8. So oic acid becomes O8, okay? And then you also list the cation. So cation comes first. So cation first. So if it's a sodium, it would be sodium benzoate. If it was a potassium, it would be potassium benzoate. Let's say it was a acetic acid salt, it would be sodium acetate, right? Or sodium ethanoate, right? That's the way you would do it there. Now, it says here that in water, carboxylic acids dissociate only slightly. So if you're not paying attention, wake up just for a second, because this is very important. If you go back again to chapter 3, if I take a strong acid like HCl and I put it in water, the equilibrium is going to lie hard to the side of hydronium plus the chloride ion. Why? Because if I compare, the pK of HCl is around -7 and the pK of hydronium is around -1.7. So remember, the equilibrium lies to the side of the weaker acid. So let's think about this. If this is my acid, my carboxylic acid, and this is my conjugate acid, which it is, the carboxylic acid has a pKa that's around 5-ish, whereas hydronium has a pKa which is around -1.7. So that means that if you put a carboxylic acid in water, it's only going to dissociate slightly, right? Remember, if you go back to the definition of a strong acid is one that dissociates virtually 100%, whereas with a weak acid, it only dissociates slightly, right? It's a weak electrolyte. And so if we look at carboxylic acids, like benzoic acid or acetic acid or propionic acid, they all have pKa's in the 4 to 5 range. Now remember, if you're like, well, that's not a strong acid like HCl. No, a carboxylic acid, I never said it was a strong acid. I said it was an acid. It's a proton donor. If you compare a carboxylic acid like acetic acid, which has a pKa of around 5, if you compare that with ethanol, which has a pKa of around 16, okay, well, yes, then a carboxylic acid is much more acidic, right? 10 to the power of 11, okay? So that's the idea. So again, this is just rehashing it. Compared to HCl or sulfuric acid, yes, carboxylic acids are weak acids, but if you compare it to an alcohol, it sure isn't, okay? They're relatively acidic. Now, where does the acidity come from? If you go back to the idea of areo, okay? The acidity doesn't have anything to do with the atom, right? Because if you compare these two, they both have the hydrogen attached to an oxygen. It doesn't have, if you compare two carboxylic acids, let me just copy this, paste it. So I'll actually cut this out and I'll paste it over here. Okay, let me paste it here. This is where it would fit in better, okay? If you compare the pK of these 4 carboxylic acids, okay? Why is it that as we add chlorines to the molecule, they get more and more acidic? You see the pKa drops from 4.8 to 3 to 1.2 to 0.9. Why is that? It's got nothing to do with atom, because the conjugate base has the negative charge on an oxygen for all of them. It's got nothing to do with resonance, because they all have the same number of resonance forms. It's induction, right? Because as you add halogens, you're adding electron withdrawing groups. And so what that means is it's going to be better able, the molecule will better stabilize the negative charge of the conjugate base, as you add halogens. Give me a thumbs up if you're with me on that idea that's in this red box here. How that is based on induction, right? You pull electron density away, it stabilizes the molecule. Okay, so then the question will sometimes become, okay, well, what if I compare the negative charge on the alpha carbon versus the beta carbon versus the gamma carbon? Did I say negative charge? I meant the halogen. The idea is this, is that as the halogen goes further away from the carboxyl group, right, you see as it goes from alpha to beta to gamma, by the time you get to gamma, it has no effect. Okay, the electron withdrawing group has no effect. It only has an effect at the alpha position or the beta position. Also, if you have an electron withdrawing group, right, an electron withdrawing substituent, and we looked at a lot of those in chapter 18, those are going to affect the benzoic acid as well. So here we have an electron withdrawing group that is para to the carboxyl group. Well, if you have a nitro group, that pulls electron density in, so that stabilizes the conjugate base. If you have an aldehyde, same thing. Chlorine is electron withdrawing, so on and so forth. So the idea is that as you add electron withdrawing groups, they stabilize the negative charge of the conjugate base as well. And remember, the weaker the base, the stronger your conjugate acid. All right, so what it's asking us to do in this question is, again, nothing mind-boggling. It's just kind of sorting out some ideas in our brain. But it says here, see if you can rank the following compounds in order of increasing acidity. So 2,4-dichlorobutyric acid. So let's write that one down. So we have butyric acid, which looks like this. We have 2,4-dichloro. So we have something here, and we have something here. Good. The next one is 2,3. So if we have our butyric acid, we have something at carbon 2, and we have something at carbon 3. And the last one is 3,4. So for that one, we have something at carbon 3, and then we have something at carbon 4, like that. Okay, there we go. Those are the three compounds. If I call this one, I'll call this one A, B, and C. Okay, if I go from least acidic, right, to most acidic. Could anybody tell me which one of these is going to be the most acidic? Which one has the most pronounced electron withdrawing effect? It would be A, B, or C. There's one that's going to affect even stronger than C, right? Because in C, right, if I color code the carbons, right, if I yellow, 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 right, red, 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 and then if I do this one in green, okay, maybe does that help a little bit? Okay, so we want the chlorines to be as close to the carbonyl as possible. Exactly. It's going to be B that's going to be the most acidic, right? Because the chlorines are closest to the carbonyl group, right? Then if I compare A and C, in A you both have a chlorine on the green carbon, but in A the second chlorine is closer, right? It's on the yellow carbon, so that means that A would be in the middle, and then C would be the least acidic of all of them. So most acidic and least acidic. All right. Does that make some sense? Give me a thumbs up if that makes some sense to everybody. Cha. Okay. The next one's a little trickier. All right. We'll call this compound, I don't know. Let's call this A, B, C, D, and E. I'll walk you through this one. Now, there's one that is by far the most acidic, okay? And that's the one with the strongest electron withdrawing group. So if we look at all these groups, we've got a bromine, a nitro, an anisole, so a methoxy, we've got a methyl group, and then we've got this thing here. Well, remember that we said that a bromine was deactivating, right? But it could donate by resonance as well. The nitro is a strong deactivator. So we'll put here a strong deactivator. This one is actually a moderate activator. So moderate activator. This one here is going to be a weak activator. And this one here is going to be a moderate deactivator. All right. And then the halogen is going to be somewhere in the middle because it's a deactivator, but it's the weakest of all the deactivators. All right. So with that, whichever one is going to be the strongest deactivator, that one's going to withdraw the most electron density. So if we put here, I'll write it down in blue, we'll put most acidic, most acidic. Okay. The most acidic one is going to be B for sure, followed by E, right, which is also a deactivator. Then the two other ones that I put in here, these are activators, but the bromine is a deactivator. It's not strong, it's weak. So then it must be the one with the bromine on it. So now, if we go between C and D, which one of these is going to donate the most electron density? It's going to be C. So that means that D is going to be here, followed by C, like that. Okay? So this rationale came from chapter 18, is how I kind of solved that one. All right, now, have we seen how to make a carboxylic acid already in this class? The answer is, oh yeah, we've seen it a few times. So it says here in earlier chapters, okay, we saw some carboxylic acids being synthesized. So let's take a look at those examples. The first one comes from chapter 9. If you had an alkyne and you cleaved that using ozonolysis, you would end up with a pair of carboxylic acids. Also, we said that if you oxidize, remember this is called the Jones oxidation reagent. Okay, that word is not in our textbook, but that's what it's called. Okay, if you use chromic acid, which is generated by sodium dichromate, sulfuric acid, and water, you can convert a primary alcohol to a carboxylic acid. And then the last one showed up in chapter 17, okay, is benzylic oxidation. So this is benzylic oxidation, right? So for that, you just use chromic acid as well. You can use a two-step process using, for this one, you could also write or KMNO4, water and heat. I could do heat better. Heat followed by H3O plus. That will work as well, but that's benzylic oxidation. So we have seen the synthesis of carboxylic acids in this chapter. And I want to tell you that you've also seen it when we looked at a cyanohydrin. If you guys remember, like last chapter, we had a problem where we took a cyanohydrin like this and we hydrolyzed it with aqueous acid, and we ended up with this carboxylic acid that looks something like this. So that is not a new reaction, and so we know that you can hydrolyze a nitrile using aqueous acid and heat. Okay, this mechanism, I didn't write it down here, but this mechanism is covered later. So mechanism, I'll just put here later. Okay, we're going to look at that later. So if you hydrolyze a nitrile, that gives you a carboxylic acid. Another way is if you just do an SN2 with cyanide, right? Remember, this is cyanide. Okay, you get your nucleophilic attack, your loss of leaving, oops, that's not very good. A loss of leaving group like that. Then you can convert your nitrile to a carboxylic acid just by treating it with H3O plus, just cooking it up. Let's see here. One more thing I want to show you before we take a break, and that's this reaction here. If you're wondering what this funny picture is here down at the bottom, this is actually solid CO2, okay, also known as dry ice. Okay, you can buy that at King Soopers. In a freezer, they have a King Super. So if you take a Greenyard, okay, so this is a Greenyard reagent right here. Remember that Greenyards are good nucleophiles. So if you put it in the presence of CO2, that's what this is down here, you end up doing a nucleophilic attack and you form a carboxylate. Remember, this salt was called a carboxylate. And then you can protonate that with H3O plus. And so what's the overall reaction going to look like? Well, it's on the next slide, so I'll show you. So you would take your, in this case, it's an aryl halide. You treat it with magnesium, and you make your Greenyard reagent. And then in step 1, you treat it with the CO2. After step 1, you would have the carboxylate. You would end up with this, the carboxylate. And then in step 2, you add the proton by treating it with aqueous acid. And there you go, a new way to make carboxylic acid. So this question here says, if you had to take ethanol and convert it into acetic acid, how would you do that? Okay, well, ethanol is a primary alcohol, and so really we've only got one way of doing it, and that is to use sodium dichromate, sulfuric acid, and water. You could also do it in base, and I wrote that down before. If you use KMNO4, water, and heat, followed by treatment with H3O+. That will work too. Okay, both of those will oxidize a primary alcohol to a carboxylic acid. In the next one, you have toluene, which is methylbenzene, and if you want to oxidize toluene to benzoic acid, so you have to oxidize at that benzylic position to give you benzoic acid. And so to do that, remember this is a benzylic oxidation, and so we're going to use our same old sodium dichromate, sulfuric acid, and water. So the same conditions that we used before to do that. The next one, if I want to take benzene, and convert it into benzoic acid, come on, benzene. And I want to convert it into benzoic acid. I'll just put the benzoic acid over here. Well, I can't add the carboxyl group directly, but I could do a bromination, right? I could do a bromination with bromine and iron tribromide, right? And that would give me bromobenzene. And then all I would have to do is treat it with magnesium and then CO2 to do the Grignard to get the carboxylate. And then step 3, I would treat it with hydronium. And that's going to protonate to give me benzoic acid. So it turns out that you can reduce a carboxylic acid all the way down to a primary alcohol using lithium aluminum hydride. We don't use sodium borohydride for this, but lithium aluminum hydride. Remember, LAH is stronger than sodium borohydride. So you can take the lithium aluminum hydride and reduce the carboxylic acid all the way down to a primary alcohol. Next one is a new reaction. So this is new, and there's also no mechanism for this guy, okay? So if you take a carboxylic acid and you treat it with BH3THF, you're like, where's the second step? There is no second step for this reaction. You just treat it with borane and THF. That will also reduce all the way down to a carboxylic acid. And what's cool about this reagent is that BH3 can be used, but it's chemoselective for the carboxyl group. So that means if you tried it in the presence of this methyl ketone here, for example, it's not going to do anything on that. It's only going to react with the carboxylic acid. That is it. So brand new reagent. So now what we're going to do is we're going to take a short break, and I want you guys to see if you can come up with some syntheses for these problems here. You can see that in the first one, we're going from 6 carbons to 7 carbons. And in the next one, we're going from 7 carbons to 7 carbons, so no change in the skeleton there.